Hi, my name is Kimi Okuno from the Institute of Statistical Mathematics, Japan. Today, I'm going to talk about the Minimax analysis for inverse risk in non-parametric invertible regression. This work is joint work with Dr. Inazumi of the University of Tokyo, and this result has been published as an archive manuscript. So if you are interested in this talk, please refer to this archive manuscript. Okay. Today, I'm going to talk about the minimax convergence rate of the non-parametric regression. This slide shows the summary of this talk. In this study, we focus on the invertibility of the function. Particularly, we consider an estimation of the invertible regression function, and we also evaluate inverse risk. Inverse risk is defined as the sum of the risk for the estimation function Fn hat, this one, and the risk for its inverse Fn hat. So we consider this type of special risk, and we prove that in the case of these two, meaning that the input and output of the function f is two-dimensional, then the minimax convergence rate of this inverse risk is -2 divided by 2 plus d power of n. And actually, this convergence rate is the same as the rate for the Lipschitz function estimation. So it indicates that the invertibility is not that strong assumption compared with the Lipschitz continuity. So this result is shown in our paper, Okuno and Imaizumi 2021. Although this result is based on theoretical interest, this convergence rate can be used as a baseline of efficiency of the invertible function estimation. Okay, and furthermore, this result is only for two-dimensional regression problems, but if I further generalize this result to the arbitrary dimension D by further assuming C2 smoothness, we are now preparing this general result, and maybe we will submit this result to archive until the end of this year, so please stay tuned. Okay, so at the beginning of this presentation, I'd like to introduce the background knowledge of the invertible function estimation. In this talk, we assume that the set I here, this one, is a closed interval from -1 to +1. And we consider functions whose image and range are both these power of I. Then the function from ID to ID, meaning that the function between two hypercubes, is said to be invertible if the set defined like this is a unique point for any fixed y. We call this set by the inverse of the function f. And actually, these figures show the examples of the non-invertible function and invertible function. Please look at the left one. For instance, this function 2 times squared x minus 1 is not invertible. This is because, for instance, if y equals 1, then there exists 2y satisfying this equation. X equals 1 satisfies this equation, and x equals -1 also satisfies this equation if x equals y. Okay. And also, please look at the right one. This function, the third power of x, is obviously invertible because by taking any y, there exists only one x satisfying the equation if x equals y. And actually, as you can see in these examples, the invertibility is closely related to the monotonicity of the function in the case that the dimension d of the input and output is 1. Generally speaking, obviously, the continuous and invertible function is also strictly monotone if we consider the univariate case. And also, fortunately, from the historical perspective, there are many existing works studying the monotone functions in the field of statistics and economics. This figure shows one example. In this figure, x-axis shows the dose of medicine, and y-axis shows the response. Usually, we may assume that the response is monotonically increasing as the dose increases. So some researchers restrict the prediction function of response to be monotone functions with respect to the amount of dose. Subsequently, many researchers focus more on the monotonicity of that function, and many theories have been developed so far in the field of statistics and economics. Okay, and While the one-dimensional case, monotone function estimation is mainly considered in the field of statistics, multivariate invertible function estimation gathers much attention these days in the field of machine learning. When considering the multivariate case, the invertible function is no longer monotone, but it has one-to-one correspondence. One main application is generative models, including GANs, variational autoencoders, and so on. For instance, if we can train the function that maps several images to the latent space, and if there exists one-to-one correspondence between these two spaces, then the inverse of this map can generate new images from the random sheets generated in the latent space. And if this function from the image space to the latent space is not invertible, more than two images may be generated by inputting one random sheet in the latent space. So the invertibility constraint is a very important restriction in the field of machine learning. But it is quite difficult to define invertible estimators. Actually, we can define several invertible functions by imposing very strong assumptions. But the function may have a limited expressive power. For example, if we consider only the linear transformation as this invertible function, we can implement the invertible linear function estimation easily, but it is limited to linear models. On the other hand, if we employ an expressive model like a standard neural network, the prediction model is usually not invertible. So it is quite difficult to realize both invertibility and high expressive power simultaneously. Actually, a recent line of works proposes a restricted form of a neural network model so as to be invertible. This type of invertible neural network is especially called normalizing flow, originated from a famous paper in et al. 2014. Okay, here I listed several famous normalizing flows. I skipped the details, but commonly, most of the normalizing flow models are in the deep form like this. We may apply a simple parameterized invertible function phi and apply an affine transformation psi. And again, we may apply a simple invertible function phi, something like that. Then this function is obviously invertible, and its inverse can be easily obtained by composing the inverse of each transformation. So there are many types of normalizing flows using different phi function. For instance, Hausfelder flow employs a Hausfelder transformation for this function phi, and it is obviously invertible. But actually, these types of flows are proved to have a low expressive power. I mean, they have not universality. In these recent 2 years, several studies try to prove the universality of normalizing flows. And eventually, the affine-coupling flow, ACF, this one, is proved to universally approximate arbitrary sheet invertible functions. Okay, so please see this slide for the affine-coupling flow, which is universal. ACF is a bit complicated, but the important point is ACF still holds invertibility. Please. And ACF is also proved to be universal approximator of sheet invertible functions. So ACF attains both invertibility and high expressive power simultaneously. In my personal opinion, this result is amazing and excellent. They utilized, Teshima's team utilized very detailed knowledge used in the field of geometry, and consequently, they proved the universality of ACF is completely different approach from the standard discussion of neural networks. But however, there still remain several problems. Also, the universality is proved, its efficiency is yet to be revealed. For instance, for ACF, Teshima's group proved the universality of ACF with the increasing number of layers in the ACF. I mean, Teshima assumes that the number of layers in the ACF model should be infinite. Okay. So we are still not sure how efficient this estimation is. Even the simple minimax convergence rate is not obtained. And actually, as I explained earlier, the one-dimensional case is okay. So if we consider the one-dimensional case, the invertible function reduces to monotone function, and the monotonicity is easy enough to handle with. Many statistical papers consider the efficiency of monotone function estimation. But the multivariate setting is much more difficult. Monotonicity is no longer available, and even the characterization of the invertible function is not well known. It is quite hard to construct even non-parametric estimator. I mean, there is a huge gap from one-dimensional case to the multivariate case. Yet only a few properties is known for multivariate invertible function estimation. So we try to evaluate the efficiency of the multivariate invertible function estimation. Okay, from here, I'd like to describe the conventional theories and our problem setup. In this talk, the symbol finv denotes the set of invertible functions, and finv Lipschitz denotes the set of invertible functions f, where both f and its inverse, f inverse, are Lipschitz. So we assume that the underlying true function f star belongs to this one, the set f Lipschitz inverse. We also assume that the observations, namely the independent pairs of xi and yi, independently follow the standard additive regression model like this, y equals f star x plus epsilon, where the epsilon follows normal distribution. Then we estimate the function fn hat by using only the observations. This is our problem setting. And only one important point is that the true function f star is invertible. And we estimate the invertible function by using invertible estimator. Okay. In the usual theory of statistics, statistical consistency is defined like this. Usually, the risk function is defined by the L2 distance between the true function f star and the estimator fn hat. And the convergence rate is also defined as how fast the risk function reduces to 0. Also, the convergence rate for Lipschitz function estimate. Also, the convergence rate for the Lipschitz function estimation is very well known traditionally in the field of nonparametric statistics. And this rate for the kernel smoother is known to be -2 divided by 2 plus d powers of the sample size n. These are kind of standard theories, not considering the invertibility of estimated functions. But however, the standard theories on consistency measures how rapid the convergence is, and the consistency does not guarantee the invertibility of the estimated function. I show a small example, and in this example, we want to estimate the invertible function, and we define a sawtooth-like wave function as an estimator of the identity function. This sawtooth-like wave function obviously approaches to the underlying identity function, and the convergence rate can be arbitrarily fast, in fact. However, as you can easily see that this sawtooth-like estimator fn hat is obviously non-invertible. If you specify 1y, its inverse is obviously more than 2. So this is an example that is consistent but non-invertible. We need to modify the risk somehow to measure the invertibility in addition to the consistency, the usual sense. So to measure both invertibility and the consistency simultaneously, we employ a newly proposed inverse risk. To define this risk, we first define the inverse of the estimator fn hat. Usually, fn hat, the estimator, is not guaranteed to be invertible. So if the function is invertible at the point y, then its empirical inverse is defined as the unique inverse. And if the function is not invertible at the point y, namely there are more than 2 inverses or no inverse, then the empirical inverse is defined by the constant vector c as an exceptional case. Then we define the inverse risk as the sum of the risk for the estimated fn hat itself and the risk for its inverse, its empirical inverse. Okay, so this is the definition of the inverse risk. And here we employ a function psi. And in our theory, in the simplest case described in this talk, the function psi is specified by the force power of the argument. Okay, and this risk measures both consistency and invertibility. For instance, when we consider the example explained in the last slide, this one, then the inverse risk does not decrease to 0, while the standard risk function reduces to 0. So again, using this risk, we can measure both the consistency and invertibility. We want to evaluate the convergence rate of this inverse risk. Okay, and from here, I'd like to describe a characterization of the invertible function so as to propose an invertible and consistent estimator that reduces the inverse risk to 0. To define our estimator, we characterize the inverse functions in this slide. Here, the function f is assumed to be invertible function, and we define an output-wise level set, LFJYJ, like this. This set is defined as element x such that the function value of fjx, output-wise function fjx, equals y. Then it is easily shown that the inverse of the function f, this one, coincides with the intersection of two output-wise level sets. Actually, this output-wise level set is controlled by one parameter, so the set should be a line like this figure. I show an example, and the inverse of the function f, this one, is characterized by the intersection of two output-wise level sets. This one, this one. So the invertibility is confirmed by checking whether the intersection is a unique point or not. And as a simple example, if the function f is an identity function, then the output-wise level sets are parallel to x-axis and y-axis, respectively. So this level set representation is like a skewed Cartesian coordinate. Here I show a real example of this level set representation using a bit complicated invertible functions. Here, the parameter t controls the fineness of the grid. For instance, if t is large, there are many grids. Then the level set representation of the function are like this. You can see that each pair of output-wise level sets colored by blue and red are crossed at only one point. So we can characterize the invertible functions by using this kind of level set representations. So, and also we can obtain some properties of level sets. We skip the details here, but by assuming that the true function is Lipschitz, we can prove that the output-wise level sets have good properties, like continuity or something like that. Okay, then I explain a basic idea of the proposed invertible estimator. To explain the basic idea of the proposed estimator, I first explain the simple univariate case. In this univariate case, meaning that the dimension d of the function input is 1, then the invertibility is closely related to the monotonicity of the function. However, usually the estimated function is not monotone. For instance, if you employ some existing regression models, like a kernel smoother or K-nearest neighbor or neural network or something like that, then the predicted value is not always monotone, even if the underlying true function is monotone. Then the function output may include a perturbation. Please see this figure. If we try to approximate the invertible monotone ground truth function by some estimator, then the estimator may have fluctuation like this. So this function is not invertible, but our idea is simple. Our estimator is a two-step estimator and ours modifies the arbitrary consistent first estimator, such as kernel smoother and kernel smoother estimator, to be invertible. Please look at the right figure showing the proposed second step estimator in the invariant case. As you can see, in this estimator, we first compute the first step estimator at 5 points here. This one. Then we interpolate the first step estimator linearly, and the interpolated value is our proposed estimator. Then, as you can easily say that the modified second step estimator should be invertible in asymptotic sense, because we linearly interpolated these points. There is no fluctuation here. This is a piecewise linear function. Okay. So here I'd like to generalize this estimator to the multivariate case, and our proposed estimator is simple. Similarly to the invariant case, we first compute the level set representation over the grid by using the first step estimator. Then we have a kind of skewed grid of the function, and then we can find some quadrilaterals like squares. Then we can interpolate these squares similarly to the invariant case. And then we can use these interpolated values as the second step estimator. So our estimator is like smoothing of the first step estimator. This is our proposed estimator. Okay, we show some numerical experiments here. Please look at the left figure. And the left one is the ground truth function, a heat image of the ground truth function. And then we generated the 10,000s of observations with some noise. And then we computed the first step estimator using these observations. Please look at the center one. The figure in the center represents the first step estimator. And as you can see, the first step estimator contains some fluctuations. And actually, this estimator is not invertible because of this fluctuation. However, as you can see in the right-hand figure, the second step estimator removes this fluctuation by using the interpolation. So as you can see, the second step estimator is much more smoother than the first step estimator. And actually, this estimator is invertible. Okay, the next experiment shows that the estimated functions with different parameters. The parameter t here represents how many of grids are used for interpolation. Then you can see that using large T, we have smoother functions. And the bottom figures show the grids used for the interpolation. We computed these grids inside our estimator. And this slide also shows the heat map of the predicted functions when the underlying true function is different. As you can see, the proposed second step estimator shown in the right figure is smoother than the first step estimator shown in the center figure. Okay. From here, I'd like to describe briefly the lower and upper bound analysis of the proposed inverse risk. Okay. As a result, firstly, we could prove that the lower bound of the minimax risk for inverse risk. Actually, we skipped the details here due to the time limitation, but anyway, we can construct an invertible function by using some level set representations. And then we could prove that the inverse risk is lower bounded by this rate. And actually, this rate is the same as the standard Lipschitz function estimation. This is the lower bound analysis. And on the other hand, we could also prove that the upper bound of the minimax risk of the inverse risk is like this one. Actually, as you can see, this rate is compatible with the lower bound up to the logarithmic factors. So we can finally obtain the minimax risk up to the logarithmic factors. And actually, the proposed estimator described in the last slides attain this convergence rate. Here I skipped the technical details, so please refer to our paper if you are interested in these rates and derivation. Okay. And at last, I'd like to explain the ongoing work and conclusions. So far, I explained about the convergence rate of the inverse risk for Lipschitz functions. And actually, the dimension of the function is restricted to be 2. But, this assumption is a bit restrictive. So we generalize these results to the general dimension by further assuming sheet smoothness on the underlying true function. Then we could prove that the inverse risk is also upper bounded by the same convergence rate. Please look at this table. Our previous study, which we wrote 1 year ago, considers the two-dimensional Lipschitz inverted functions, but our ongoing work considers general dimension by assuming that the underlying function is Q times differentiable and smooth. Now we are writing a paper for this result, and we hope to submit our paper until the end of this year. Okay, this is our conclusion. We considered an inverse risk for regression problems estimating the Lipschitz and invertible functions. We proved in two-dimensional case that the minimax rate of the inverse risk is like this one. And actually this rate is compatible with the minimax risk of the standard Lipschitz function estimation. We also proposed a minimax optimal estimator that attains this convergence rate. Okay, thank you very much for listening.